4 of you are there. Shall we wait for some more time? Let people join. Right. Shall we start, guys?
Yes, sir.
Okay. So I think we have been doing periodic table, right? Okay. So I think last class we saw how do we go about your ionization enthalpies, right? So we spoke about what is ionization enthalpy, how is it varying along the period, along the group. We saw what is first ionization enthalpy, second ionization enthalpies, right? And we even saw something about electropositivities, metallic characters, and obviously electropositivity means the ability of the element to form positive ions. And how will they form positive ions? By losing electrons, right? So we saw how that electropositivity is going, is varying down the group and along the period from left to right. All that we saw. And then I even connected this with your reducing power, because I know electropositivity means elements will lose electrons, right? So I know in terms of oxidation and reduction, right? Loss of electron is oxidation and gain of electron is reduction. So in this case, electropositivity, elements are losing electrons, so they are undergoing oxidation, right? So what kind of agents they would be? They would be reducing agents. Whichever is getting oxidized is the reducing agent, whichever is getting reduced is the oxidizing agent. So all that we saw last class, right? Okay, so we'll go on to the next concept, right? Next trend in the periodic table, and that is my electronegativity, right? Or I would see first some other, or let's see this first, right? All right, okay, fine. I'll see electronegativity only, no problem. Okay, so we already know what is electronegativity, isn't it? At least we have studied this about in your periodic table of 10th class, right? Okay, so how did we define electropositivity, right? The same way I will be almost same way I'll be able to define electronegativity also, but in this case it is going to be in terms of negativity. There it was electropositivity, right? Please check down the definitions. Please check down the definition for electronegativity. It is the ability of the element. It is the ability of the element to attract a shared pair of electrons, to attract a shared pair of electrons towards itself, right? So it is the ability of the element to attract a shared pair of electron towards itself. That's what is electronegativity. So from the definition you can understand what I'm trying to tell. So it's basically electropositivity is the ability of the element to lose electrons, right? Here in case of electronegativity, it is the ability of the element to accept electrons, right? It is the ability of the element to accept electron, right? So what do you mean by the shared pair of electron? It comes in the covalent bonds. Say for example, if I have HCl or say HF, something like this, right? So all these are HF and HCl, you know, these are compounds of acids, right? Okay. So I know, like I would say chlorine and fluorine are little highly fluorine is the most electronegative element in the periodic table, isn't it? Right. So now what is going to happen? Now you already know in a covalent bond there are two electrons shared, right? In a covalent bond there are two electrons shared, one from hydrogen, one from fluorine, right? So if you think that this two electrons, where exactly these electrons are going to be present, right? So for like I will take one more example actually. I'll take H2, HH bond I'll take, right? Okay, so here also I have a shared pair of electron, right? Okay, so here if I check where exactly the shared pair of electron is present, right? If I check where exactly the shared pair of electron is present, it is going to be at the exact center of these two atoms' nuclei, right? These two hydrogen atoms will have a nucleus, right? So this shared pair of electron will be somewhere exactly in the between these two hydrogen atoms' nuclei, right? It will be exactly in the center of these two nuclei, right? Because these two are equally electronegative, right? But if I go for a bond like this, right, I would say fluorine is more electronegative. So what is going to happen? This shared pair of electron which I have is not going to be at the center, right? This shared pair of electron is not going to be at the center because fluorine has high pulling capacity of electrons because it is highly electronegative, isn't it? So fluorine has more pulling capacity of electrons. So these two electrons are not going to be at the center of the nucleus like this. It will be actually, in this case, it will be more and more towards fluorine, right? It will be more towards fluorine, little far away from hydrogen. And this is what I say. It is the ability of the element to attract a shared pair of electron towards itself. So this is the shared pair of electron towards itself. In a sense, fluorine, it is going to move towards fluorine because of its high electronegativity, right? So that is how I properly explain electronegativity. Or in simple words, right, I can say that electronegativity is the ability of the element to accept electrons. Very simple, right? It is the ability of the element to accept electrons. That's the simplest way I can put it, right? Okay, so now we have to understand how it varies along the period, how it varies along the group, right? So now it is all about accepting electrons here, right? So whatever you saw for electropositivity, right? Well, whatever you saw for electropositivity, the exact opposite you are going to see for electronegativity, isn't it? Now tell me, what happened to electropositivity down the group? Guys, what happened to electropositivity down the group?
It increases.
Exactly. It increases. So metallic character basically increases down the group and it decreases along the period, right? So it is going to be exactly opposite for electronegativity. So please understand, down the group, right? Down the group, that is lithium, sodium, potassium. If I go down the group, the electronegativity value decreases, right? Electronegativity value decreases, right? Say for example, if I compare fluorine, chlorine, bromine, iodine, these are the halogens family in the same group, right? So if I want to arrange them in the order of electronegativity, what will happen? So I would say that down the group it is decreasing. So fluorine will have more electronegativity than chlorine, than bromine, than iodine. This would be the order of electronegativity, right? So if I compare from period, like say if I say carbon, nitrogen, oxygen, fluorine, right? Now along the period, what will happen? For electropositivity, it was decreasing, right? So for electronegativity, it would have been increasing. So along the period, right, my electronegativity value increases, right? So obviously fluorine will have more electronegativity than oxygen, than nitrogen, than carbon, right? So this would have been the order of electronegativity along the period. So just like how I connected certain other chemical properties with electropositivity, like that I'll be able to connect certain other properties with your electronegativity also, right? So for electronegativity, I can also call it as non-metallic character, right? It's also called as non-metallic character because generally non-metals will form anions, right? So here we are accepting electrons to form negative charges, right? So obviously it is going to be called as non-metallic character, and electropositivity it was metallic character, right? Okay, and one more thing I'll be able to connect in terms of oxidation and reduction. And just now we spoke, oxidation is loss of electron, reduction is gain of electron, and that's what is happening here, right? F, for example, F will accept an electron to form F minus, right? Fluorine will accept an electron to form fluoride ion, right? Okay, so what you're saying here is reduction process. Is it not acceptance of electron or gain of electron, right? So if this is undergoing reduction, it is definitely going to be an oxidizing agent. So whichever undergoes reduction is the oxidizing agent and vice versa, isn't it? So in this place, it is undergoing reduction. So whichever highly electronegative elements are generally good oxidizing agents, and highly electropositive elements are actually good reducing agents because they are undergoing oxidation there. Now here they are undergoing reduction. So I can even connect this with the oxidizing power. What do you mean by oxidizing power? Ability of the element to act as an oxidizing agent, right? How much power it has to oxidize something else, right? And I already told you, like, it's oxidizing agents or reducing agents are going to do that in a sacrificial way, isn't it? Okay. So all these three things down the group, it decreases along the period, it increases. No problem. Okay. Right. So we'll move on to the next one. Right. Now, just like that, how we spoke in terms of energy. For example, for electropositivity, I told you that the energy equivalent is my ionization energy, right? First ionization energy, second ionization energy, all those we spoke. Now here again for electronegativity also we have an energy component, right? So that is the next trend we are going to see. So I think it's easy, everybody understood. Right. So the next one is what is called as electron gain enthalpy, right? Or it is also called as electron affinity, right? Electron gain enthalpy or electron affinity. Okay, fine. So again, we have to take the definition first, right? See, please understand this, right? If I speak about ionization energy, right? If I speak about ionization energy, right? So obviously, I'm going to take out an electron. So for take out an electron from the valence shell, right? So I obviously have to supply energy, right? I obviously have to supply energy, isn't it? Because I have to overcome the force of attraction between the nucleus and the electron, isn't it? I have to overcome the force of attraction. Already the electrons are strongly attracted by the nucleus, right? So I have to supply energy so that I'll be able to overcome this force of attraction and then take out the electron, right? Okay. So in chemistry, right, there are certain sign conventions you follow, right? There are certain sign conventions you follow. Always remember, energy supplied or energy absorbed, right, will always be a positive value, right? For example, I say that 100 joules of energy is absorbed or 100 joules of energy is supplied to the system. I say then it should be plus 100 joules, right? The value should be positive whenever you supply energy, right? And whenever energy is released, right? Whenever energy is released, right? So I say that that value should be negative. This is the standard sign convention we follow in chemistry. So for example, if I say that during a process, some 100 joules of energy was released, right? So for mathematical purposes, I will be using that energy value as minus 100 joules. Right? So the magnitude is what that matters. The sign is just indicating whether the energy is released or whether the energy is getting absorbed, right? So the magnitude is what does matters. So you should not say, for example, in this case, electron gain enthalpy, I would say some of the elements are going to have a negative value, right? In electron gain enthalpy, some of the elements will have what is that? A negative value. So what does it indicate? Whenever I'm adding an electron, right, some kind of energy is going to get released. That's what it says, right? Whenever you see a negative value, and some of the elements will have positive value also, right? That means what? For that particular process, I have to supply energy. So that's what you need to understand. Okay, but positive or negative, the sign doesn't matter actually. Only the magnitude matters, right? Because sign just indicates whether the energy is absorbed or the energy is released, right? So this 100 is what is important, not the minus 100. Yeah, minus 100 is important to indicate whether the energy is released or absorbed, but for your comparison purposes, the magnitude is what that matters. Okay, okay, fine. We'll take down the definition for electron gain enthalpy. Please take down. It is the energy change occurring. It is the energy change, or you write like this. it is the energy absorbed or released. It is the energy absorbed or released when an electron, it is the energy absorbed or energy released when an electron is added to the valence shell. When an electron is added to the valence shell of an atom. Right? When the electron is added to the valence shell of an atom. Right? So it is exactly opposite of ionization energy. Is it not? I told that in case of an ionization energy, it is the energy required, by which I'll be able to take out the electron from the valence shell. Here I'm adding the electron. So obviously when I'm going to add electron, right? So either energy is going to get released or energy is going to get absorbed. Okay, now how do we decide that? Right? How do we decide whether what to say? Energy is getting absorbed or energy is getting released? That's what we need to understand. Right? Fine. So what do you understand by energy getting absorbed? That means for me to add an electron to a particular atom, right? And I see that the electron gain enthalpy value is positive, right? For example, you see for sodium, right? It will be actually a highly positive value. The electron gain enthalpy will be a highly positive value. What does it indicate? It indicates that for me to add an electron to sodium, right? I have to actually supply energy. Right? I have to supply energy. So that means it's very difficult, right? But for example, say for chlorine, right? For chlorine, you will see that it is actually a highly negative value, right? It's understood that it is actually going to be a highly negative value. So what do I understand from this? If I add an electron to chlorine, right, that process is very, very easy, that I don't have to supply any energy. The energy will become released. The energy will be emitted. That's what we need to understand. Right? Now you can ask me, sir, why is energy getting emitted? Right? So that question obviously comes like for this I understand. Right? If I have to add an electron, say first we'll come to this. Right? Why should I supply energy for me to add electron? Is the question. Right? So you have to understand this. Inside an atom, already there are so many electrons present. Isn't it? Inside the atom, there are already so many electrons present. Isn't it? Right. So if I'm going to add one more electron, don't you think that incoming electron will suffer repulsion between the existing electron from the existing electrons? Isn't it? The incoming electron will always suffer repulsions from the existing electron. What electron which I'm going to add, that electron and the already existing electron will suffer a lot of repulsions, right? So I have to overcome that repulsion and I have to put the electron in the valence shell. Right, I have to overcome that repulsion. Then I have to put the electron in the valence shell. So for overcoming that repulsion, only that I have to supply energy. Right, for overcoming that, I have to push the electron so tightly so that I'll be able to put it in the nucleus of the atom. Right, so that is why you see that energy is getting supplied. Right. Now, what do I understand from this? If it is highly negative, I understand that the energy is getting released. So what do you understand from this? Now there is one more term I'm going to introduce you to now. Right? It's not a new term and all, you already know it. So there is something called as stability. There's something called as stability. Right? Oh, we know what is stability. Stability means it is not going to, like, it is stable. Like, it is not going to react much. It cannot be disturbed that easily. It is stable. Right? That particular species is stable. That's what it means. Right? Okay. So now stability and energy, how they are related. Right? Now we'll speak like this. Okay. Okay, we have two persons, right? So one person is highly energetic, another person is little lazy. Okay, one person is highly energetic, another person is lazy. Okay, so now if I ask both of them, right? If I ask both of them to say go 10 rounds in a ground, I'm asking to go for some 10 rounds in a ground, right? So which person do you think will be more active for that? Obviously, the person who is more energetic, isn't it? The person who is more energetic will actually try to go around the ground how many ever times you ask him to. But the guy who's lazy, right, is not even gonna get up from his bed, right? So now whom will you call stable? Tell me. The lazy guy or the energetic guy? Did you understand the question?
No, sir.
So basically, I have two guys, right? So like say both of them are in the ground, right? And one guy is so energetic, right? And the other guy is very lazy, right? So if I ask both of them to go run around the ground, right? Obviously, the energetic guy will definitely go around because he's very energetic. The lazy guy, like he will not do much, isn't it? Right? Now tell me, in terms of stability, if I speak, who is more stable, the energetic guy or the lazy guy?
Energetic.
Energetic guy.
Okay,
Lazy.
fine. See, I have this duster, right? Say, assume that this is a guy, or this is a, I'll not say it's a girl, fine. This is a guy, okay? Fine. So I hold, basically, he's very strong, right? He's very stable, I will say, right? Now, when I try to hit him like this, right? See, he's not moving at all, right? If I try to hit him like this, right? He's not moving at all. But say he's like this, and I hit him. It went. Right? I'll take my duster. 1 second. Yes. So what I'm trying to tell you is the strong thing is stability, right? That means when I tell you to do something, and if you don't do that, it's actually stable. Because I don't want to do, like, it's like I'm already stable. I'm already comfortable in my own position, isn't it? So anything extra which I have to do, that particular species will not do, right? So like I'll speak in terms of reactivity of elements actually also, right? Say if I say that an element is highly stable, right, it is not going to react that much with some other element, right? But if I say that element is highly reactive, now it is, or let's say if it is highly unstable, then only it will try to react with something else, right? So coming back to your energetic and lazy person, obviously the lazy person is more stable than the energetic person, right? So what you need to understand from this is, if I have very high energy, the stability will actually be very, very less, right? And if I have very less energy, obviously I will not be able to move around easily. I'll be comfortable in my own position. So that means I have stability, right? So please understand, energy and stability are actually inversely related. Energy and stability are inversely related, right? High the energy, very high energy, if someone has, he'll not be able to sit at one position also, right? Very active. So that I would say he is not stable. But a calm guy who's a little lazy, right, is actually more stable, right? Fine. So why did you speak about all this is because you have to understand what do you mean by energy getting released, right? Fine. So I have some energy. Okay. Think about this. Okay. I have the same energetic guy, right? I have the same energetic guy. Say, assume that he had gone for some 5 rounds already in the ground, right? Assume that he has gone for already 5 rounds around, he ran and came, right? So now what would have happened? He would have lost all his energy, isn't it? He would have lost all his energy by doing this process, by running around the ground, right? Now what will he do? He'll go straight to the ground. He'll go lie down. That's it. Now what happened to him? He has attained stability, isn't it? The energetic guy initially had so much amount of energy, that means he's unstable, right? And he ran around the ground, he did some work and he lost his energy. Now what happened? Now he'll not be able to do anything. Even if he asks to go for 5 more rounds, he'll say, no, I'll not be able to do it, right? So now he has attained stability. How he has attained stability? By losing energy, right? But obviously high energy means less stability. So he had initially high energy and less stability, right? So by doing a process, the energy level came down, right? So obviously stability would have gotten increased, right? So that's what you need to understand. So basically, if I see that for a particular element, the electron gain enthalpy value is negative, that means by adding an electron to chlorine or a highly electronegative element, it actually attains stability. It actually attains stability, and that is why you're seeing that energy is getting released, right? But for the other one, if you see that this positive, actually it is, now what do you understand? It is already stable, right? These electropositive elements are highly stable. Now, if I'm going to add an electron, to this, definitely I have to supply energy. So it's like making the lazy person somehow run. What will I do? I have to push him to run. I have to supply energy for that guy to run, isn't it? Same analogy here. Sodium is highly electropositive, right? So it's okay. I would say sodium is already stable, right? So now you're adding an electron to it. That is not possible. So I have to supply energy to that. But chlorine is little unstable, right? Chlorine is little unstable. By adding an electron, if it forms Cl minus, it's actually stable, right? And that is why you see energy is getting released. So by losing out energy, that Cl minus is going to attain stability. Okay. So guys, did you understand the correlation between energy and stability? Everybody understood?
Yes, sir.
Okay. So the stories you don't have to remember. The only thing you have to remember is energy and stability are inversely related. That's what you need to understand. Okay. Fine. So now we'll see how it's varying down the group and along the period. Your electron gain, enthalpy, or electron affinity, right? Okay. Fine. So lithium, sodium, potassium, for example, I take these three examples and see how is it varying, right? So again, it is going to depend on the size, isn't it? Right? Okay. Actually, first we'll see what are all the factors which will affect the electron gain enthalpy value. So obviously, the first factor would be size. Right? First factor would be size. Now you tell me, I have a small atom, I have a very big atom. In which element adding electron is easier?
Big atom.
Why?
Because it's huge in size, so the nuclear forces of attraction would be less.
If
And the
nuclear
valence
forces of
electron.
attraction, if nuclear forces of attraction is less, see, there are two things here you have to look at, right? One is the electronic repulsion. Between the incoming electron and the existing electron, I can have repulsion. Okay. And there can be attraction also, where from what to what? From the nucleus to from the nucleus inside and the incoming electron which is coming, I can have some force of attraction. Right. Now think and tell me which force has to dominate for electron gain enthalpy to be highly negative value. Repulsive forces or attractive forces?
Attractive force.
Obviously, attractive force has to dominate. If the repulsive force are dominating, the electron will not be able to go inside the atom because it is highly repelled. It is pushed away from the nucleus, right? But if the nuclear force of attraction is very, very high, right, then I can understand that the electron can be easily added. We have to keep an electron in a place. The nucleus itself, it is going to take it inside. Correct, right?
Yes.
So now tell me. Now look at this and size.
And small.
And tell me.
Small atom.
Obviously, right? So when I have a smaller atom, it is actually easier for me to add an electron because nuclear force of attraction will be very, very high, right? So generally, size and the electron gain enthalpy will be inversely related. That means what? Smaller atoms, I'll be able to easily add electrons, so amount of energy released will be very, very high, highly negative values. Okay, right? Fine. Next one, size is done. Next one is about charge density. It's about charge density. Okay, what do you mean by charge density? Charge density means charge divided by size. Nothing. Charge density is nothing but charge of the element divided by size of the element. Okay, anyways, charge density in the sense for a small, how do we say? We say population density. What do you mean by population density? For 1 kilometer, in a radius of 1 kilometer, how many people are there? That is what is population density. Same way, I'm going to in a particular size of an atom, how much charge is there? That is what is called as charge density. Okay, fine. So what will happen is, even though sometimes the size is smaller, right? Even though sometimes size is smaller. Or for example, I'll take an example. I'll actually take fluorine and chlorine. Okay. Now think and tell me, which do you think is going to have higher electron gain enthalpy? Fluorine or chlorine? Out of fluorine and chlorine, which do you think will have high electron gain enthalpy?
Fluorine.
Fluorine.
Yeah, we expect fluorine, isn't it? Because fluorine is smaller in size, fluorine is more electronegative, correct? So we expect fluorine to actually, have a high electron gain enthalpy. But you know what I see in reality? I see that chlorine's value is greater than fluorine's value. Chlorine's value is greater than fluorine's value. Even though chlorine is bigger in size, right? What I understand is adding an electron to chlorine is little easier than adding an electron to fluorine, right? Can you come up with an explanation for this?
The valence electron fluorine has more.
Both of them same valence electron, right? They belong to the same period, sorry, same group. They'll have 7 valence electrons, fluorine and chlorine.
Our charge density will be more for fluorine.
Charge density will be
More for fluorine.
more for fluorine. Okay, so because of that, what happens?
Increases. Then
So repulsion will increase.
Yes, that's the term I was looking for, right? So again, it's all about attractive forces dominating or repulsive forces dominating, right? So in fluorine, since I have a very small space in that so many electrons are there, the incoming electron will suffer lot of repulsion. The incoming electron will suffer lot of repulsion, right? But in chlorine, I have little bigger atom and I have some number of electrons. The charge density, basically the word which I have to use is charge density. Charge density for fluorine is very, very high because it has some amount of charge in a very small atom, right? So, but in chlorine, it is little bigger and the same charge, -1, obviously, right? So there the repulsion, or say there the charge density is less, right? So if I'm going to add an electron to fluorine, smaller size, higher charge, the incoming electron will suffer a lot of repulsion, right? So it is very easy, it is easier for me to add an electron to chlorine rather than fluorine. This is actually an anomaly. Okay, fine. Same goes with my oxygen and sulfur also, right? Oxygen and sulfur. So again, oxygen atom is smaller. So I expect easily adding electron to oxygen atom because of high nuclear force of attraction. But because of high charge density, right? Because of high charge density, that is smaller atom, bigger charge, right? The incoming electron will suffer again repulsion. So sulfur is actually going to have more electron gain enthalpy than oxygen. Okay, so anyways, these two are the, and obviously one more thing which I have to look at is half-filled stability also, right? After this, I have to look at half-filled or fully filled stabilities. Right, we know what is half-filled and fully filled stabilities, isn't it? Okay, so keeping all this in mind, right? Keeping all this in mind, I'll be able to easily tell you how it varies along the period and how it varies along the group, right? So obviously, so I can say that down the group, right? Down the group, electron gain enthalpies will decrease. Why? Because size is increasing, right? Down the group, size is increasing, right? So electron gain enthalpy value decreases. Okay, fine. So along the period from left to right, obviously size is decreasing. So adding an electron is going to become easier. So my electron gain enthalpy value increases. This is the general trend, right? This is the general trend, but I can have like this assumptions also, right? Actually, these two are the only assumptions, right? For electron gain enthalpies. Anyways, so along down the group, it decreases, the electron gain enthalpy value decreases, and along the period, it increases, right? But there are assumptions for fluorine, chlorine, and oxygen, sulfur, right? So let me look into that groups. 1 second, please. So I have fluorine, chlorine, bromine, iodine, right? So if I ask you to arrange them in the order of electron gain enthalpy values, so this is how we arrange. Now I generally what I expect. I expect down the group the electron gain enthalpy value must decrease, right? But only for these two elements there is going to be a change. Why? Because fluorine, the high charge density is there, the incoming electron will suffer more repulsion. It is inter-electronic repulsions. Because of that only fluorine. Now you have to write very, very properly, guys, in your school exams. You have to give the proper explanation. You have to say like, fluorine is very small, so it has very high charge density, and in the incoming electron will suffer high inter-electronic repulsions. So it is very tough for us to add the electron there. That is why the electron gain enthalpy value of fluorine is lesser than that of chlorine. Like this, you should write it. Okay. So anyways, so now what will be the order? The order would be chlorine, fluorine, bromine, iodine. This would have been the order of electron gain enthalpies. Okay, right? Right. So if I ask you, I have oxygen, sulfur, fluorine, chlorine, right? Oxygen, sulfur, chlorine, fluorine, and I ask you to arrange them in the order of electron gain enthalpies. Can you tell me the answer?
You can repeat the question again.
I have oxygen, sulfur, fluorine, chlorine, right? Arrange them in the order of electron gain enthalpies.
Chlorine, fluorine, sulfur, oxygen.
Okay, so it should be chlorine, fluorine, sulfur, oxygen. Yes, that's the answer. Right? Okay. So yeah, hope you understood how is it happening. So the only for fluorine group, fluorine and chlorine and oxygen and sulfur, you have this anomaly. Other than that, these two holds good. Down the group decreases, along the period increases. Yeah. Right. So this will hold good. So that is about electron gain enthalpy. Okay, so is there anything else in this chapter which I have to see? Yeah, that's it. So the chapter is over, guys. What is the time? Okay. Any other thing which I have to size? Okay, we can have one more example for this. Say I have carbon, nitrogen, oxygen, or carbon, nitrogen, oxygen. Okay. Now, if I ask you to arrange them in the order of electron gain enthalpies, what would have been the answer?
Carbon, nitrogen, oxygen.
They're telling oxygen is going to have maximum.
Sir, because in the case increases, no sir.
Yeah, I understand. Right. So oxygen is going to have maximum. That is correct. What about nitrogen, chlorine? So nitrogen, carbon.
Nitrogen, carbon, sir. Okay, carbon and nitrogen.
Tell me the reason, man. Like, why it happens like this? Yeah. So actually, the answer is this. Nitrogen comes after carbon. Why?
Nitrogen is half fill stability.
That's it. Yeah, nitrogen is having half fill stability. That's the reason. I know in nitrogen I have 2p3. Right? So imagine I'm actually adding an electron. You see, already electron size like this. In the same shell, I have to add the electron here. So much repulsions will happen. Correct? Right? So yeah, so this would have been the order of electron gain enthalpies for oxygen, nitrogen, carbon, nitrogen, fluorine. Carbon, nitrogen, oxygen. Okay, right? So we'll try to solve some examples. We'll try to solve some problems. Actually, we have solved almost everything. Yeah, so we have almost solved everything, right? So yeah, guys, that is about the chapter, right? So how was this chapter, guys? Was it Better than last chapter? Or
Yes,
okay,
sir.
okay than last chapter? Okay, fine. But still my favorite is atomic structure. Okay. So this is little there and there funky, interesting, but atomic structure is still scientifically very interesting, isn't it? Right. I think we have a new student today. I think it's Venisha. Venisha, are you there, Venisha? Venisha, you can unmute yourself and speak.
Sir,
Yes, Kana. So which school are you from, Kana?
Sri Chaitanya, sir.
Oh, Sri Chaitanya. Okay, so you're studying Techno CBSE.
Yes, sir.
Okay. So how was the class? How did you feel the class was?
It's nice, sir.
Did you understand everything?
Yes, sir.
Right. So if you don't understand anything, it is just because you're new, you don't have to pause. You don't have to stop yourself. You can always ask your doubts.
Okay, sir.
You'll be added in your groups also, right? So I
Mm.
think you would have been in the group. You can ask your doubts in the groups also, or here.
Yes, sir.
Anything
Mm,
is fine. So welcome to Epsilon.
Thank you, sir.
Yeah. Okay, guys. Any other doubts from any of the previous chapters? Like we have completed how many chapters now? Some basic concepts, atomic structure, periodic table. 3 chapters we completed. So any question you solved somewhere, anything which you studied you didn't understand, you want me to ask now, you can ask. Go for it.
Sir, I have one question, sir.
Yeah.
Sir, how many subshells are associated with n equal to 3 and how many electrons would be present in the subshell having a spin of 1/2 negative?
Okay. Fine. Easy. We'll do it. So yeah, the first question is I have n is equal to 3. They're asking how many electrons can be placed here. That's the first question.
Yes, sir, how many
Oh, how many electrons can be placed with a spin of -12, isn't it?
Yes, sir.
Okay. So if I have n is equal to 3, I know L value can be 0, 1, 2. Correct? So what all I can have? Basically, I can have 3s, 3p, and 3d. This is what I would have had, right? So in 3s, 3p, and 3d, right? Now he's asking how many electrons can be there with a spin of -12 or +12, doesn't matter, whatever it is, right? So what I have to do, I have to put only one electron. Say if I fill all the electrons here, 1, 2, 3, 4, 5, whatever. Okay, so all the electrons I have filled, right? So in this S, how many electrons are having +12 spin? S subshell, you tell me.
1.
1, right? So +1 here. Here, how many electrons are having +12?
3.
3. Here, how many?
5.
5. Totally, how many? 5 plus 3 plus 1, 9 electrons.
9.
That's the answer for your
You
question.
can explain again, sir, for me, current and top, sir.
Yeah, sure. So basically, n is equal to 3, right? So n is equal to 3 means I can have L values from 0, 1, and 2. That means S, P, and D, all 3 are there. Correct? So S will have 1, P will have 3, D will have 5. I have filled all the electrons here, right? Now they're asking how many electrons can be there in this shell, right? With a spin of -12 or +12, doesn't matter, right? Now in this S subshell, right? How many total 2 electrons are there? Out of these 2 electrons, how many electrons are having +12 or -12 spin?
One.
Only one electron. Here in p orbital, there are totally 6 electrons, and how many of them are having -12? Only 3 of them, right? And in D, I have 5 of them, totally 9.
Thank you, sir.
Okay. Any other question, guys? Just bring it on.
Sir, the test we wrote, sir,
Okay.
on the first question.
Okay. What is the question?
1 minute, sir. Check it.
Yeah. Take it. So others, you can ask your doubts till he asks.
Yes, sir. With what velocity must an electron travel so that its momentum is equal to that of a photon of wavelength lambda equal to h by mv?
Okay, so lambda is equal to h by mv. They're asking what should be the velocity of an electron so that it has an energy.
Momentum is equal to that of a photon with the above wavelength.
Okay, momentum of a photon with above wavelength. Okay, okay. So mv, momentum of an electron of this wavelength, right? Oh, this is h by p I can have, right? I can
Okay.
have h by mv is h by p. This is what is momentum, right?
Yes, sir.
So I have to find what is the velocity. And that's it, right? If I know the momentum, right? And momentum is equal to m into v. Basically, here it's mass of electron. Mass of electron value is what? 9.1 and 10 power minus 31 kgs,
Yes,
right?
sir.
Into the velocity, that is the momentum, is equal to this value. Can you found here? You can find the momentum value actually from this. That is will be h divided by lambda.
Yes.
Lambda value have they given?
No, sir. They haven't given lambda's value. They've given momentum of a photon
Momentum of a photon
having
moving
this
with,
wavelength.
that's what, having this wavelength. They have not given the wavelength value, isn't it?
Yes, sir. Not given the wavelength value.
Okay. What is the velocity of an electron which is having an momentum equal to a photon having this much?
Should we substitute mass and the mass of a photon, sir?
No. Mass of photon is basically mass of electron. It's same only. Just can you just one more time please repeat the question?
Okay, sir. With what velocity must an electron travel so that its momentum is equal to that of a photon of wavelength lambda equal to h by mv?
Oh, they're just giving lambda is equal to h by mv.
Yes, sir.
Okay. So what velocity the electron has to travel?
Sir, actually, this question we wrote in the test, sir. Chemistry test we wrote, sir.
Yeah. Chemistry. That's where only. That's from that only he's asking actually. H by. So this velocity of electron and the velocity of photon is same. That's what they're telling, right? So as the velocity of a photon, which is having a lambda value is equal to h by mv. So this v, how will I write? I can write it as h by m lambda, right? So h by m lambda. So this is actually going to be equal to h divided by m lambda. Yeah, that's the only thing I can say, because the velocity of electron should be equal to the velocity of a photon, which is having this much wavelength. So this is say velocity of photon, but velocity of photon is zero, right? Sorry, mass of photon is zero actually. Okay, look into it now. So I don't think you need some numbers for you to answer this question. It is just going to be in terms of h and lambda, because they didn't give you any value, isn't it? So it should be in terms of these letters only. Like it should be in terms of h, m, and lambda only, right? You're not going to get any number as the answer for sure. Anyways, I'll check the solutions.
Okay, sir.
Right, but anyways, you're not. I'm sure that you're not going to get any numbers as the answer. It is just going to be this symbols only are going to be there, right? Okay. Any other question? Any other question? So next class we'll be starting with chemical bonding. Okay. So chemical bonding is again a very, very interesting chapter, and it is a very, very important chapter, not with respect to marks, right? But with respect to understanding the structure of a molecule, right? So we are going to deep inside the elements, and we're going to deep inside the compounds and see which bond is stronger, right? Which bond is weaker. And we'll be seeing, for example, if I have methane, right? What is the shape of the methane and why that shape is taken place, right? And obviously we spoke about stability. We'll be speaking so much about stability, different kinds of bonds, ionic bond, covalent bond, coordinate bond, hydrogen bond. So many types of bonds are there. You'll be studying about them, right? And yeah, you will be able to get a lot of insights about what a bond is, right? What are the different types of bonds? All these things we'll be studying in the next chapter. Okay, so I think it will be on Monday. Okay, so till then, any other doubts, guys? Shall we wind up the class?
Yes, sir.
Right, fine then. Thank you so much. We'll meet again. Bye
Bye.
bye. Yeah.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.